Hello everyone, so welcome back. This is a video that we're going to talk about the resampling methods in chapter 5 of our textbook. So today we are going to talk about a validation methods. So mainly focus on two approaches. The simple one is called the validation set approach, and the other one is the cross-validation approach. So in today's lab, we are going to demonstrate how to do the cross-validations here. So first of all, we are going to use the library ISLR package. So we load that, and we are also going to use the bootstraps in the next videos for doing the bootstrap resampling. So today we are going to use the autos data set. So if you do not remember what a auto data set is, you can actually call it out. So the auto data sets basically is one of the data sets in the ISLR package. So the data sets contain the variable of mileage, the mileage per gallons, cylinders of the car, displacements, horsepower, and weight of the car, and accelerations and such. And we are going to plot these two variables here by using the plot functions, the mileage per gallon versus the horsepower. And obviously we see this very consistent results of downward sloping behavior of the data point. So the higher the horsepower, the lower the mileage per gallon it is for the car. So first, we're going to take the validation set approach. So the whole idea for validation set approach is to create two subsets of data from our original data, and we call them one of the data sets training data sets, and we call the other one the testing data set. So the first process, it's always trying to create a random seed, and we are going to generate the random sampling index so that we can actually use the index to call out the data sets from our original data set. So we basically save this sampling here. So we're using a sample functions. We're picking some number randomly. Well, we are going to pick number within the dimensions of the data set. So if you do not know what the dimensions of the data set is, so if you use the dimensions functions auto, it will return you the dimensions of the data set. So the data set has 392 rows and 9 columns, and we only need to define the row number here. So we want to define the first number, right? Remember the indexing methods, we're using a square brackets to basically retrieve the first number in this report results, in this output, which is 392. So we are randomly selecting numbers from a dimensions of 392. Out of the 392, we would like to select 300 random numbers from the index 1 to 392. We randomly select just 300 random numbers. So we save it as a train, and let's see which 300s we get. So right here. So we randomly select the 300 numbers from index 1 to 392. The first number we draw from the index is 324, and the second number we randomly select is 162. The third number it's 129, and so on. As you can see here, there is no number, it's repeated. So when you're using a sample functions here, we're basically doing a random sampling with no replacements. So once we have the trainings index saved, and we are going to basically use the linear models to basically model the mileage per gallons with horsepower. So we have the mileage per gallon as a response variable here, and the horsepower as a predictors. And we're using a data set auto, And here, this is one very convenient parameter you can pass into this LM functions. You can call out which subsets of the samples that you want to use for training the models. So in this case, I actually call the subsets equals to whatever the trainings index that I pass in. So those are the index number that I'm going to use in my models. So for example, in this subset, I will have the 324th rows to be my first observations, 167th rows from our original data set as my second observations, and 129th rows in my original samples to be my third observations. And it basically just use it as a index call to basically let the LM function knows which rows from our original data sets that we want to use to train our models. And we save it as the fit one. So this, so far, well, there's nothing very fancy here. We're basically just using a subset of samples to basically train our model. And we can now print our summary of the models. And seems like horsepower, it's very, very statistically significant. And obviously, we can see it from the graph that we plot earlier. So once we're getting the model trained, the next thing that we want to do, again, in this chapter, we are not focusing on modeling the data. We are not trying to find the fits of the data, but instead, we are trying to use a technique called validations technique to see how well the model can predict the unseen data sets. So now, what we want to do, it's basically trying to calculate the mean square error. So here, we actually use the mean functions, right? We want to take the average of the squared error. So the squared error basically calculate by using the MPG in our data sets minus the predictions of MPG from that particular observations that we pass in the data to basically make a predictions. So for instance, the first one that we are trying to predict should be using from our original data sets the 324th rows of data to pass into our model and trying to make a predictions of the mileage per gallons to basically get an estimate. So the 324th rows will have a number of horsepower. So it goes into the model, fit one, and then it will run the predictions. It will return a number. And we go back to 324th rows to basically see what is the actual values of MPG for that particular horsepowers of the car. And then we subtract the two and we square it. So here, very important for you to note, we are using this square brackets here to basically identify we are only using the training data sets to make our predictions. So this mean square error we are calculating is basically the training error. So again, by indexing here, right? So the square brackets, we're indexing which observation we want to use from our data sets of autos, and then we try to make a predictions and compare it to the original data set's values, and then square the terms. So we can see what the result is. So the mean square error returns 23.911 here. Again, if you are still not familiar with the concept of mean square error, it's basically how far your predictions away from your actual values of response, but we are squaring the distance of the difference. So that means, well, this number should be relatively large as comparing to what you might actually see in the graph. But it doesn't really matter. It's a very, very reliable measure. So that's usually what we use to compare about the training's errors and testing error from our models. So now we calculate the mean square error, right, for the training sets, and we want to know how well fit ones, our model trained with the training data, will handle the unseen data set, which is whatever data that we did not pass into fit ones, right? So the data that we don't use to fit the model, and now we want to try to make a predictions and compare to its actual results. So we are using again the same functions, mean functions, and this time we are using the mileage per gallons minus the predictions using the models, and we do not include, right? So we see the negative signs here basically means we subtract, we're subtracting those index numbers from our data sets. So we delete those rows, and the leftover must be what we have as a testing data set. So we are basically testing our models, fit1, to see how well it fits the unseen data sets that it's not being used for training. So let's see what's the mean value here. And as expected, this value should be larger. Most of the time should be larger than the training error. So the reason is because the trained model, it's basically trained in a way to fit the training data set so that it can make the minimum error with the data, with the training data indeed. However, whenever we have some unknowns, new data observations that we pass into this fit and trying to make a predictions, because the model have never seen this data before, and obviously the model will sometime actually make a mistake, and it will happen a lot more often comparing to if the model is facing the training data sets. So the error term here for the testing error will be much larger, which is what we expect to see. So now, if we move on to say, hey, what if we want to play around with this technique and trying to see which model it's better to predict our testing data. And we can now try to say, we want to maybe adding one additional term here, which is adding a square terms to horsepower. So we are using the polynomial functions here. So here, the polynomial functions, the POLY brackets, basically it's a wrapper. It wraps two things together. It wraps the the horsepower variables, right, the columns, and it passes in this 2 into the polynomial functions and indicates that we want to have 2 degree of polynomial. So that means we have the horsepower with no power, right, just or maybe to the power of 1, and plus the horsepower with the square terms. So we fit this model and we find the summary of it, and now we can see that we have the first power of the polynomial functions and the second power of the polynomial functions, and both of them are statistically significant. So that's why, well, it makes sense, right, to give it a try. And now let's see what we can get out from our trainings error. So the mean square error for the training data, again, we indicate it here, right? We are indexing, we're using only what included in the training. We got 19.38974, which is much better comparing to the previous model. Well, which somehow you can tell because, well, the second term that we add here, the square term that we're adding here, it's also statistically significant. So that means it definitely will improve the fits of the models. Now, the thing is, can it do better to reduce the testing error too? So when we actually using the square term, not only it improves the training's error. In this case, seems like even though we are passing in some testing data into our model for predictions, we can even better to predict the results. So that's basically indications that this model fit maybe is a much better one to use in order to predict the unknown data sets in the future. And now, well, since we're adding the square term, well, why don't we try the cubic terms, right? So we're now using a polynomial functions as a wrapper in this linear models, and we are trying to define to have 3 degree of polynomial. So we include the horsepower to the power of 1 to the square of the power, and the third powers in the linear models. So we run this, and we print the summary. And as you can see, I have the 3 polynomial terms right here. And the first 2 terms still statistically significant. However, the third term doesn't seem like adding much value to our models. And it's not statistically significant at all. As you can see, the p-value, it's extremely large. So let's see how well it predicts. So if we are going to predict the training data sets, well, it still outperformed the linear functions because, well, we still have this very low training error terms here, 19.35. Well, as comparing to the previous, well, it's not as well as it does, but definitely it's a better one than the linear. All right, so let's see the testing error term. So the testing error term, again, well, it's going to be much lower comparing to the linear functions where we have only power to the ones, and this time 17.685 comparing to the previous seems like we're doing a slightly better. Again, even though we are doing a slightly better in this example here, it doesn't really mean that we necessary to add this third degree of power into our linear model. The fact that, well, by adding this term into our models, the degree of freedoms actually decreased by 1 more units, and the predictions that we are getting, right, the accuracy rate that we are getting, it's not as much of a improvements here. So basically, we can actually ignore and not adding this third power to our linear models, and just stick with the second degree of polynomial functions would be good enough for making a good predictions in the future, based on the validation set approach. So that's basically the way how we run the validation set approach, right? We split the data into just 2 sets, right? The training set and the testing sets, and then we test it with the testing set to see how well it predicts the unknown data. Now, of course, one particular questions that arise as you actually learn from the class, or maybe from your readings, is that, well, the validation set approach is not a very dynamic way to test the data. Especially, it's very, very likely that you might actually accidentally picking a set of data randomly from your original data sets, that it's going to be a group of outliers. And the outliers will definitely increase the error or your testing error when you're training your model with the ordinaries observations. So the outliers will definitely tell you the opposite of the story of how well your model actually predict the unknowns. However, there is no controls of how well you are randomly selecting one set of samples from your original data sets. And that's why we are going to basically cover another approach, which is a much more popular approach, much more useful, both mathematically and also technically, that give us a much better results in validations procedures. So the first one we're going to go over is called the leave one out cross-validations. So the term cross-validation here basically means that we are going to validate our testing error not just one time, but we are going to do it multiple times. And now the question is, how are we going to do it multiple times? So the basic idea is, if you actually have a set of sample, you can actually split this sample data sets into two groups, right? The testing and the training. And go to the extremes, you can actually separate out only just one observations from your sample sets to be your testing sample, right? Only one. And the leftover, all the other samples, data or observations will be goes into training the models. And then you test it with this one observations and see how well it fits this one data point. Now the question is, if you can actually go to this extreme, can you actually do it multiple times to see how well your trained models with majority of the data and how well it predicts this one testing observations? And if we repeat them over and over again, we keep using the one observations, right? We take the first observation out and test it, and then we take the second observation out and test it again, and the third one and the fourth one, and go on and on and on. Can we actually get a general idea how well the models make a predictions of a unknown data? So that's basically the whole idea for leave one out cross-validations. The term leave one out basically means we are leaving just one observation out and having all the data sets to train the model, and we are going to test only just one observations to get an idea. And then we keep repeating the process until we're running out of sample to leave out from our data sets, and then we will try to aggregate all this testing error together and see how well the model predicts the unknown data sets. So to use the cross-validations, we are going to use this cv.glm functions. So if you are not very familiar with these functions, again, you can always ask R to define it for you. So there's a whole documentations of these functions here. So basically, you need to pass in the data. You need to define the GLM fits, and you have to define the cost and also the K term, well, how many folds of classifications, cross-validations process. And later we're going to cover. So let's keep it a simple case. So first of all, what we want to do is to fit our model into a general linearized models. So we're using the GLM functions here. We're fitting the linear model, MPG, as our response and horsepower as our predictors. And we're using the whole data sets here, which is the whole auto data sets. This time we are not separating the subset here. So we have to use the whole data sets to do the fits. So we save it as a GLM fit. And then we're going to run these functions here. So we're going to run the cross-validations functions, cv.glm. So in this case, basically the function cv.glm will do the cross-validations for us. And it will basically run the GLM model for n-1 times. N, it's basically your total number of observations. And then you can actually get the one of the parameters out, one of the return measurements out, which is delta. So let's see what it returns here. So we run the models, and it will return this two data, delta here. So the delta value here, it's basically telling you there are two error terms that you get. The first error term here, it's basically the error term for your training data sets as a whole, right? So everything included. And the second number here basically reports the cross-validations error terms in this test. So as you can see here, you will be able to get some measurements, how well the cross-validations error compared to the model itself. So again, the delta contains the validations results, and it gives you the convenience to see how well the leave one out statistics will or the leave one else methods to help reporting the error terms for explaining the fits of the results. So the delta cross-validations predict the errors, and it gives two numbers. The first number is the raw leave one outs validations error. Again, the second one is the bias error. That's due to the fact that the data set that we trained on is slightly smaller than the one that we actually would like to get the error for. So as a full set of data ends. All right, so now what we want to get from this leave one out cross-validation method also is trying to get a very good idea about, well, how well the models will fit our data, especially the unknowns data, right? So we are going to create a functions here. So we call this a LOOCV functions. So the leave one out cross-validation functions. And this function will basically just pass in a fit of the model. And it will generate lm.inference to the fits here. And it will report this number and save it into this h variables. And after that, we are going to use the mean value. We get the average with residual fits divided by 1 over h. So this is basically the equations that's given in the textbooks 5.2. So this is this h right here. It's another way how we can easily get the cross-validations results. As you can see before, calculating the cross-validation using the cv.glm, it's going to take you quite some amount of time because, well, it just looped through the whole data set and trying to pick one out and then do the fits and then trying to test the error, and then it picked the second observation, put the first one in, and then trying to run the fits, and then trying to make a predictions and getting the error term. So it will be a lot longer if you have a data sets that contain many rows. So in order to reduce the computational time, there is another way to do it. Well, this is basically the functions. So the h term right here basically is the inference factors that we use for our calculations of leave one out cross-validations. So in this equations, you only need to run the fits of the model one time. So this function here only run the fitting process one time and only getting the parameters, right? This coefficients here, h, one time from your full model, and then plug into these equations using the residuals divided by 1 over h squared to get the cross-validation results. So again, well, if you are curious about how to use it, I'll just save it and trying to run this leave one out cross-validations with the GLM fit that we use that we previously did in the cv.glm functions. So we do it, and it returned the result pretty fast. So the cross-validations standard error in this case, not standard error, but the testing error will be 24.23151, which is exactly the same as we seen from our cv.glm functions. So if you prefer to use these functions, of course, you can actually copy this and reuse it as many times as you want. Just save it, right? To run these functions before you running your cross-validations test error, and then you fit the model in there, and it will automatically generate the results. But one thing that's worth to note, this functions right here does not generally apply to all the statistical methods that we learn in this class. And to be more specific, this particular functions only work in the linear regression functions. So that means if you have a linear regression functions that you want to test the leave one out cross-validation error, you can use these functions. However, if you are if you are doing a classification model, let's say a logistic regression models, or maybe LDA models, unfortunately, these functions will not work. It will not work. So you have to keep that in mind. This is mainly just for the linear regression models to make to reduce the amounts of calculations. So it's not generally applied to any models that we do. All right, so let's try to do something different here. Let's suppose we are interested in doing a leave one out cross-validations, and we would like to test the cross-validations error with 10 different models. So we want to actually test how well different degrees of polynomial terms will help improve the cross-validation error. So in this case, we first save an empty array here. So we're creating an array of data, which is an array with 10 positions, and each position has a number equal to 0. Right? So basically it's 10, 0 we're creating here. And we define the degree, it's an array from 1 to 10. So we have array here, degree, right? So which contain number from 1 to 10, and we have the cv.error, which is all the 0 we're saving here. And what happened in this for loop here is we want to actually run through the degree, which is 1 to 10 in this for loop. The first loop will actually pass in the first number in this degree array, which is 1. So 1 will pass into this line right here. As you can see, well, I have D defined here. So that means the 1 will goes into this positions. So we are basically trying to build a linear models with MPG as a response, and we are using a polynomial terms here, horsepower with power of 1, which is only just a linear equations. MPG equals to beta 0 plus beta 1 times horsepower. And we're using the whole data sets. And after we save the models into glm.fit, we are going to pass in the glm.fit into the leave one out cross-validations equations that we actually created earlier. Right? This functions here, we're reusing it, we're recycling it, and we save the results, the error results, into the cv.error array. And this time we are using a index method here. So again, you see the square bracket here. So D will have a value of 1. So that means this error results will save into the first positions of the cv.error array. So that means it's replacing the first positions 0 with this result here. And then after this loop, the first loop, it will go back and trying to retrieve the second number in degree, which is 2, and then it will pass into these lines. So we are going to have a 2 degree of polynomial functions. So we have beta 0 plus beta 1 times horsepower plus beta 3 times beta 2 times beta 2 times horsepower square. So we have the square term here. So we save it as glm.fit again, and then we will pass in this glm.fit into the lose one out cross validations, and we'll get the error returns, and we will save it to this time we don't have 1. Okay, we are saving it to position number 2 because D represents the number that we are retrieving from degree. So this time in the second loop we have the number which is equals to 2. So we are replacing the second positions in this 0 arrays with the results of this leave one out error by a 2 degree of polynomials. And as you can imagine, this will go on and on, right? Keep repeating, right? Floating back and retrieve the third number, and then the fourth number, the fifth number, and sixth number, and then the last one will be retrieved in degree will be the number 10. So let's try to run this for loops. Okay, so we save it. Right? It's super fast. It's super fast because we are using the LOOCV functions that we create. This is the shortcuts functions that we use in textbook 5.2 to calculate the CV error. And now you can actually print out the CV error. So in the first degree of polynomials, we have an error term 24.23 from our CV cross-validations approach. In the second degree, we have 19.248. The third degree, 19.33. The fourth degree, polynomials, 19.424. Well, obviously, we can actually keep reading this number, but what is a better way to handle this number is to plot this number with the degree that we define in the models. So here, we are using a plot functions. We are plotting out the total degree that we defined, which is from 1 to 10. And then we are going to pass in this CV.error, which is all this number that we just got from the for loop. And then we are basically using type B, which is the types of graph that we are going to use. And as you can see, we can actually have a very good understanding about how well each degree of polynomial term handle the cross-validation error. And in this graph, obviously, well, the results, it's not surprising. When we get to the degree of polynomial to the second terms, which is the square term, the error that we are getting from a cross-validations approach, it's already getting to a very, very low level. By increasing the degree of polynomial terms, at some point, obviously, we are getting to a very low number, even lower number, but obviously, it's nothing much of an improvement comparing to our second degree polynomial functions here. So that's why by this example, we can definitely make conclusions that the second degree of polynomial term probably is good enough to make a predictions for the unknown data in the future. Well, one downside about the leave one out approach is that, well, it requires the programming software to run the model fits just so many times. It depends on how many observations you have, right? So it's not always we can apply the cheating LOOCV functions because it's only used for the linear model. So when we actually having troubles to deal with, let's say, a data sets with millions of rows, and obviously we cannot ask our computer to make a model fit and predictions 1 million times, because we'll be just sitting in front of the computer and not doing anything. So the better way to do this cross-validations, well, we have an alternative here. Basically, we can try to cut up the data into different boxes. And each time we are taking out one of the boxes at a time so that we can use it as a testing data set. And then we leave all the other boxes into the trainings for training the models. And then we repeat. So the advantage for cutting up the data sets into boxes is that we can actually control how many times the computer will have to fit the model. So for instance, if we are using a tenfold cross-validations, so what we mean by tenfold cross-validations, basically it means we cut up the data sets into 10 random boxes. So each box will contain a random observations from the original data sets, and we will have the first box leaving out of our model as a testing set, and we have the other 9 boxes of data will be used to train our model. Well, in this case, with a tenfold cross-validations, we are not actually running the model as n many times as our observations suggest, we are running the model fits only 10 times, and we are only getting the error terms from our models 10 times. So to give an idea how we do this, well, we are going to basically use this example. So we are going to save an empty array with 10 zeros here. And we are going to run through the for loops here. So we are going to use the for loops to run the degree of polynomial terms again. Right, so everything on the second line here is the same. We are trying to do the LGM fit with the polynomial functions using the dataset auto. And now what we are trying to do here is using the cv.glm functions instead of the leave one out cross-validation functions. And this time we specifically defined which data we are going to use and which model fits we are going to use, and as well as which number of folds that we are going to apply to the cross-validations process. And this time the k equals to 10 basically demonstrates we want to use 10-fold cross-validation. We cut up the data sets into 10 different boxes, and we do testing only just one box at a time, and we will go back to the data and get the second trainings with 9 other boxes and taking out the second boxes out as a testing set, and then repeating until we're using up all the boxes. And again, well, we can retrieve the error term from delta, right? So delta is one of the return elements from the cv.glm functions. But this time we only care about the cross-validation error. So we are retrieving the first number from delta and save it into the cv.error10, this array of numbers. So let's run this and see what we get. So we're using the 10-fold cross-validations to run through 10 different degree of polynomials functions, and the error results returns here. So we get the first 10-fold error, cross-validation error equals to 24.0975, very similar to our previous. So when we have a linear functions only, the error term will be the largest. When we're adding the square terms, right, the second functions, right, the square functions that we use to make a model fit and test it with the data sets, the 10-fold cross-validation error tell us we have 19.27. And then we have the numbers go on and on. So again, well, to see how well it but how well the model actually fits the testing data sets, we can plot it out. And this time we are adding it on top of our previous graph so that we can compare it to the leave one out results. So we are calling the degree, and then we are passing in the error into the graph. And this time we are going to use a red lines to plot in the same graph. So as you can see, we have a very similar result. So it's very exciting at this point because that means, well, we don't actually always need to use a leave one out cross-validations. The 10-fold, which is a much shorter versions, much simpler versions of cross-validations formats, can also produce a similar result compared to the leave one out results. So at last, we would like to actually try to do the 5-fold cross-validation to see if it also comparable to a 10-fold. Right? So a 5-fold cross-validation is even simpler results or process in this case, because we are only cutting up the data sets into 5 boxes, and then we are trying to do the modeling 5 times and doing the error only with 5 boxes of data. So that's why in this case it's half amount of the works that the computer will have to do for you. So again, well, similarly, we do the same thing. We first create an empty zero arrays so that we can store our results. And we're going to pass in the degree, right? So with the GLM functions, so we will have the functions running degree from 1 to 10. And we are going to use the cv.glm functions to get the cross-validations error. We are passing in the data. We are using the glm.fits, which is we save here in the loop. And then we are going to define the k parameter here, k equals to 5. That means we are using a Fifo cross-validations. And again, we are getting the error results from the cv.glm. And we are only getting the cross-validations error terms, which is the first number in delta. And save it to a cv.error5. So run this, and we will get a cv.error5 returns with 10 numbers. So the first degree, which is the linear terms, will have the error, cross-validation error term equals to 24.121. The second number returns 19.37215, and the third one's 19.08923, and so on and on. Again, we are going to plot this fivefold cross-validations with the same plot. So together with the black lines and the red lines, so that we can compare how the fivefold cross-validations will calculate the error terms compared to the previous two. So we plot it with a line with the blue lines, and again, well, we are almost getting the same results. Right? So the first term, it's always going to generate the highest error. Starting the second degree, which is the square term, we are going to get probably the one of the lowest error we can get. And after that, well, adding the third degree, the fourth degree, and fifth, sixth, seventh, eighth, ninth, 10th degree of polynomial term does not really significantly improve or reduce the error terms from our models. So obviously, well, in this case, what happened is it's basically providing you a very good visions of how you're using this tool. Again, it's always good to have the repeated process as many times so that you can actually get a general idea how well the model is trained by different data sets will generate a different result. But if the tenfold, fivefold cross-validations also give you a similar results, then you should not actually have your computer doing this insignificant computations and wasting time to get the leave one out cross-validation results. So again, is it always the case the fivefold cross-validations or tenfold cross-validations will be as competitive as the leave one out? You probably always have to test it yourself. You always probably have to take a look of yourself to see and check whether it improve the result, or does it have a consistent results that you're getting, so that you can actually make a final conclusions which model you should use. And in this case, all three cross-validations approach, including the validation set approach, actually consistently telling us we only need the square terms to be included in our models. We do not need to expand our model further to a third degree polynomial, fourth degree, or furthermore. So now this is basically the way how we select the most efficient model for running your predictions of a unknowns or unseen data in the future. All right, so again, well, this whole lessons here, it's a very useful tools that you're learning so that you can apply to the future chapters. So in the next chapter especially, we are going to use the cross-validations and bootstrapped methods for improving the tree predictions. So that's why I would strongly suggest everyone to get on top of this chapter 5, start reading the textbook, ask questions if you don't understand it, and let me know if you have any questions about using the tools in R for cross-validations. So I will see you guys in the next videos.